Okay, composition of compounds. When we look at the chemical formula and we know the molar masses of the elements that make it up, we can figure out the relative quantities of each element in a compound. And that can be very useful in certain situations. One way to express the amount of an individual element is by looking at a mass percent composition, or sometimes just called the mass percent of an element in that compound. So of this total mass, what percentage of that mass is from this one particular element? This is the general formula for percentage. A percent is equal to the part that you're interested in, divided by the whole thing times 100. And if you learn that, you can reason and derive your way out of a lot of percentage problems, if you just understand what a percentage really is. So if we want the percentage of a compound, say compound X, percentage of an element X, which there isn't one, element X in a compound, we're going to take the mass of X in 1 mole of that compound and divide by the mass of 1 mole of the compound, multiply by 100 so that we can get a percentage. We can do that very easily if we know the formula of the compound. We don't always know the formula, though. We can also get the percent composition by analyzing the compound, essentially destroying the compound, breaking it down into its elements, and figuring out, well, what mass of X was in this compound? I know the starting mass. You take the mass of X, you divide by the mass of compound that you got it from, you multiply by 100. If you do that for each element in a compound, they should add up to 100. It's not always going to be perfect because of rounding and experimental error, but it should be close at least. Okay, let's do an example. Acetic acid is the active ingredient in vinegar. Calculate the mass percent composition of oxygen in acetic acid. There's no numbers in this problem. So we can't write down numbers. So then we'll go and what are we asked to find? Mass percent oxygen. Okay. So we're looking for the percent oxygen in acetic acid. So that's going to be the grams of oxygen divided by the grams of C2H4O2 times 100 to make it a percent. They didn't give us any masses. So what we're going to do is we're going to say, well, what would be easy? What would be easy is to find the mass of 1 mole of this, right? The percent composition does not change if you have more or less sample. It stays the same. So we're going to choose 1 mole. So I'm going to find the mass of 1 mole of acetic acid. So that's just the calculation we learned how to do. 2 times 12.01 plus 4 times 1.008 plus 2 times 16. My calculator is showing me 60.052. That's the mass of 1 mole. Now, in this problem, we don't have any experimental data numbers to limit our significant figures. So here the sig figs are going to be limited by the number of sig figs that I'm using in my molar masses. So this is going to be 4 sig figs. Okay, so that's the mass of the compound, 60.052 grams. What is the mass of oxygen in that compound? It's this part right here, right? So I wrote out my work to calculate the molar mass. You know, I did that on Wednesday too. What is wrong with me? Oh, I didn't mean to do that. Okay, this button. There. Okay. There's two of them. Maybe that's what it is. I don't know. There's two oxygens, right? Thank you. So I wrote the workout, and now all I have to do is pick the term that matches the element I'm trying to get. And you could stick 2 times 16 up here, or you can go ahead and do the math. I'm just going to do the math. 30 grams. Yeah, 32. Apparently I needed a little more weekend. Oh, just. And there's a good example of why you should not do math in your head. So since we use 16.00, that also has 4 significant figures. Multiply by 100. So we've got 32 divided by 60.052 times 100. And my answer should have 4 significant figures. 53.2871%. And so I'm going to be getting rid of the 7. That rounds the 9 up to a 10, which rounds the 2 up to a 3. So 53.30%. Somehow that seems like it was different than what I did on Wednesday, but I don't know. Oh, that's because I wrote the number wrong. It's 28. Rewind. Well, that doesn't seem right. I should have had today off too. Absolutely. 53.29%. Any questions? We can also use a mass percent as a conversion factor. Because when we talk about a percentage, that means how many of this thing out of 100, right? 75% of the population means 75 out of every 100 people. So percent literally means per 100, percent per 100. So if we look at this Freon 112, here's this chemical formula, and we're told that it's 69.58% chlorine by mass. We can take that number, 69.58, and make it into 69.58 grams of chlorine per 100 grams of compound. And now that's a great conversion factor, between chlorine and the Freon 112. So what mass in grams of iron 3 oxide contains 58.7 grams of iron? Iron 3 oxide is 69.94% iron by mass. Well, let's write numbers down. We have 58.7 grams of iron. And then we've got this 69.94% iron by mass. And what are we trying to find? The grams of iron 3 oxide. The words get kind of long. Let's figure out what that formula is. Iron 3 would be Fe 3+. That's what the 3 means. And oxide is oxygen, and we know from its position that it's a 2-. So if we do our crisscross charges thing, we get Fe2O3, which is a little shorter to write than iron 3 oxide. So this percentage means 69.94 out of 100. And that 100 there is considered an exact number. The uncertainty is in the 69.94. Out of exactly 100 grams, 69.94 grams are iron. So you can put the unit gram in here. You could put pounds, milligrams, kilograms, metric tons. As long as the unit on the top and the bottom agree with each other, are the same, it doesn't matter what the unit is. They cancel each other out. So this is grams of iron per 100 grams of the compound Fe2O3. So when I'm trying to get from iron, I'm just going to rewrite this as F. I'm going to try to get from grams of iron to grams of Fe2O3. I can do that in one step using this conversion factor, because it gives me that relationship. .7 grams of iron. So I want grams of Fe2O3 on top, and I want grams of iron on the bottom. I'm letting the units tell me what to do. So I've got the units to work out, and that tells me where to put these numbers. I'm going to take this 69 and put it on the bottom. And the 100 goes on top, because that's what I need to do to make the units work out. So 58, turn on the calculator. 58.7 times 100 divided by 69.94, 83. We should have three sig figs here, 83.929. Rounding that to 83.9 grams of Fe2O3. Is that a reasonable answer? Is it possible? This is the mass of the whole thing. This is the mass of the part. The mass of the part has to be smaller, and it is. You could make lots of mistakes and still have it be reasonable. But any questions? Yeah.
So I'm just kind of missing how the percentage was used. Because I get that the 69.94 grams of Fe is the part of the whole, and you're making the whole 100. And then you're solving, like you flip the...
I'm just using this as a conversion factor.
Okay. Oh, I see. You're making that equal to that.
So this is equal to that.
Got it.
And there are other ways you can do it.
Okay.
You could say, well, it's 0.6994 grams per gram. That's fine too. There are also conversion factors that we can get from the chemical formula. The chemical formula gives us a relationship between how many atoms of this to how many atoms of that. It does not give us mass relationships. It gives us relationships between amounts in moles or particles. Right? If we look at this formula, C2Cl4F2, in 1 mole of this compound, 1 mole of C2Cl4F2, there are 2 moles of carbon, because that's what the formula says. In 1 mole of that, there are 4 moles of chlorine. We could also write one for fluorine, right? So it'd be 2 moles of fluorine per 1 mole of the compound. Those are exact numbers, because this molecule is formed by exactly 2 carbon atoms, exactly 4 chlorine atoms, exactly 2 fluorine atoms bonded together. It's the sort of thing we use for stoichiometry, yes. Okay, let's do this problem. Determine the mass of oxygen in a 7.2 gram sample of aluminum sulfate. So we've got 7.2 grams of this compound, Do you think we're going to need the formula? Yeah, I think so. Yeah, aluminum has a 3+ charge. Sulfate has a -2 charge. So that's going to be Al2 SO4 3. And so that's the thing we're given. We're asked to find grams of oxygen. So identify where we're starting, where we're going, and then we'll figure out how to get there. We're not given a mass percent. If we were, we could go directly from one to the other, but we're not given that. You could calculate the mass percent and then use it, but that's not actually any faster than just doing it this other way. This formula gives us relationships between oxygen and the compound in terms of moles. So what we have to do is we have to go from grams of the compound to moles of the compound. Because then the formula tells us how to get to moles of oxygen, and then we can go from moles of oxygen to grams of oxygen. Now, oxygen is one of those diatomic elements. Should this be O2? See, I can't remember if I told you or the other class about this. So this is disturbing, right? Somebody's saying it should, because there it is. Okay, but is this oxygen actually by itself? No, it's in this compound, right? So the going out in pairs, never going to the bathroom by yourself, the junior high girls, that only happens when they are alone. If they're in a crowd, a group of people, like here, like this is some group date or something, everybody's going to a party, then they're fine because these oxygens are with sulfur and aluminum and everybody's all hanging out together. So here we're not going to have O2. We're just going to oxygen, the atoms, okay? Well, there's my path. So let's write out the equation. 7.2 grams, Al2, SO4, 3. And yes, it's very tedious writing that formula over and over and over again. Times and line, times and line, times and line. So I'm going from grams of aluminum sulfate to moles of aluminum sulfate to moles of oxygen to grams of oxygen. And then I work out the units. So down here I've got, moles of that monster. Be nice to just call him Al, but can't do that. Units are all taken care of. Well, this one in the middle is actually the simplest. How many moles of oxygen are in 1 mole of the compound? 12. Because the SO4 is in parentheses with a 3 on the outside. So the 3 multiplies everything inside. So there's 12 moles of oxygen to 1 mole of the compound. Over here, we have oxygen, the element. So that one's easy. We just look at the periodic table. 16.00 grams of oxygen per mole of oxygen. And then we have to calculate a molar mass. We calculate molar masses a lot. Okay, so we have 2 aluminums, 2 times 26.98. And we have 3 sulfurs, 32.07, and 12 oxygens. Two times 26.98 plus 3 times 32.07 plus 12 times 16 342.17. It's a big molecule. Well, it's a big formula mass, because the formula unit is large. 342.17. We could argue about how many sig figs are in that number, but look at what we're starting with. There's only 2. It really doesn't matter here. Just write them down. At most, there's 1 extra. Okay, so 7.2 divided by 342.17 times 12 times 16. I should have 2 sig figs in my answer. There's 2 and 2 more digits. So 4.0 grams of oxygen in 7.2 grams of the compound. Any questions?
Why was it only 2? Oh, because we started out with 7.
Because we started with 2.